Hey there, everybody. So what we're going to be taking a look at in this video here is how to determine the volume of a two-dimensional figure as it's rotated around a line, creating a three-dimensional shape. But we're going to be revolving this figure around a line that is not the x or the y axis. And that's very similar to things that you've seen previously in calculus when we were finding volumes of three-dimensional shapes where we took a figure, rotated it around a line, the x or the y-axis, creating a three-dimensional looking object, and then we were able to find the volume using either the disk method or the washer method is generally how they're referred to. Well, this is going to be very, very similar to that in the fact that we're still going to be finding the volumes of something that's going to be revolved around a line. The difference is that the line is no longer going to be just the x or the y axis. So the concept is still very similar to things that you would have seen, particularly with the washer method, but they're not going to be completely the same because we have to be able to make sure where the line is in order to correctly identify what the length of the radii are going to be for the inner radius and the outer radius that are going to make up the washer for our volume approach. So that's what we're going to take a look at here in this first example. If you notice, it's telling you specifically that it's going to rotate around a horizontal line, and this line can be kind of any, horizontal line, positive or negative. It's just some horizontal line on the graph somewhere. And because we're going to be revolving it around a horizontal line, then that means we're going to integrate it along the x-axis, meaning this would be where our interval will come from. We'll get our interval along the x-axis and see what we wind up with. So because this is going to be very similar to the washer method, we'll go ahead and review that here in just a second. But let's take a look at the functions, what we have. So the main function you need to be able to graph is the parent function, the square root parent function, y is equal to the square root of x. And so we're not going to try to get any kind of specific, accuracy here. We just know that it's going to have a shape, something along those lines. And of course we have, let's see what the other lines here are going to be. We have the y is equal to 0, which is the x-axis here, and we have the line y is, I'm sorry, not y, but x is equal to 4, and we'll just kind of draw in the line about here. So that'll be x is equal to 4, and that'll give us, let's go ahead and put some points here. So at this point right here, this would be at 4, 0, because that's where the line x is equal to 4 comes from. We are at the origin for our parent function, so you can already kind of see that the interval is going to be here from 0 to 4 on the x-axis, and that was not a very nicely written 4. Let me write that again. And let's see, points, we have a point of intersection here, and that would be at 4 and 2, because when x is 4, y is 2 on the square root function. And so the region that we're going to be revolving around some line is going to be this bit here. This is the region that we're going to be revolving around the line, and specifically we're going to revolve it around the line y is equal to 4. So let's go ahead and identify that one. So this bit right here, that is the line y is equal to 4. And so what we're going to do is we're going to take that thing and we're going to rotate it horizontally. We're going to rotate it kind of in that direction. And you can kind of see that as you did that, you're going to have an inner radius and an outer radius that are going to be created. In fact, let me go ahead and pick a different color here so things don't all start blending together. This bit right here would be the inner radius, because that's going to be the part that's closest to the line that we revolve around. Whereas this is going to be, and that's not a very well written R, we distinguish capital R for the outer radius and a lowercase r for the inner radius. And that's how we identify what the radius for the inner circle and the outer circle are going to be, because based off of where the line of rotation is going to be with the lines that create the boundary of our region. So looking at the function here, the outer radius is going to be, essentially it's going to be 4 units long. And as a way of thinking about it is you can take the line, the horizontal line where it's located, in this case it's at y is equal to 4, and you're going to subtract the other y line that it kind of goes to, in this case the when y is equal to 0. Uh, and this, I don't want to try and overcomplicate things for this one, but because you can very clearly see that the outer radius is going to just be 4 units long. But that's essentially what you would do, is you would kind of take the difference of where the line of rotation is, and you're going to take away whatever the line of, the boundary line that makes up your region. And so the inner radius is going to essentially be the same thing. And this one, it might make a little bit more sense, because if you notice, and let me just kind of highlight that here, kind of in yellow or something. The inner radius here is going to be between the line y is equal to 4, but the boundary that it's created here is not a line. It is the parent function y is equal to the square root of x. So the inner radius is going to be the difference of the line of rotation and the boundary that's created by that function, the square root of x. And of course that one won't simplify, so we would just leave that as our the value of our radius. Now the method here, as you can see, we're very much going to be using the washer method approach here. So if you needed a quick refresher on what the washer method is, let me go ahead and go to a different color here. So the volume using the washer method is going to be the integration from A to B. Oops, and I'm forgetting. Give myself a little bit of space here. Because pi is part of the, we have a circle, we're going to be finding volume of a cylinder essentially. Pi times radius squared times the height. Pi is going to be that constant, so it's going to be kind of outside of the radicand. So A to B. And then what we say here is we're going to say the outer radius squared minus the inner radius squared. And in this case, we would say dx, because that is where our interval is going to be taken along, is along the x-axis. So we've established what our interval is. Okay, so moving on, I'm going to say volume is equal to pi, and we'll do our interval from 0 to 4, and we just do some substitution here. So the outer radius is going to be 4 squared minus the inner radius, which we'll put that in parentheses, 4 minus square root of x squared dx. We need to simplify our integrand. So 4 squared is going to give me a 16. And here I'm going to subtract. Now, somewhere off to the side, you may want to just take a moment to factor. I'm sorry, not factor, but to FOIL, distribute the binomial that you have there. But when you do, you're going to get 16 minus 8 radical x plus x dx. And distribute the negative sign inside of the integrand into the parentheses, and we'll get 0 to 4. So we're going to get 16 minus 16 plus 8 radical x plus, I'm sorry, not plus, minus x. All with respect to x. And you can see very clearly that the 16s, the two constant numbers, those are going to cancel and become 0. And so what we're going to be left with is going to be an integrand across the interval 0 to 4, 0 to 4 of 8 radical x minus x. And if you prefer, you can write it as 8 times x to 1/2 power if that makes it easier for you to when you do the antiderivative. So at this point, we are going to go ahead and do the antiderivative. We've simplified the integrand as much as possible. So we're going to get pi, and we're not going to do the integral symbol anymore because we're doing the antiderivative. And so when I do, I'm going to wind up with 16 thirds x to the 3 over 2 power, 3 over 2 power, minus 1/2 x squared, evaluated from 0 to 4. And again, I like having, and my pen is not the most accurate thing in the world, I apologize, 4. I like having the lower bound to be a 0 because, of course, when you substitute that 0 into the expressions with everything having x, it all just goes away to nothing. So substitute the 4, and I'm going to get pi times 16 over 3 times 4 to the 3 over 2 power minus 1/2 times 4 squared. And if you want to, you can say minus the 0 to show that when you substitute the 0 for your fundamental theorem, that the lower bound is just going to make everything become 0. It just, drops off to nothing. And here, just perform the individual arithmetic inside of the parentheses. 16 thirds times 4 to the 1.5 power is going to simplify to be 128 over 3, and 1/2 of 4 squared will be minus 8, and then we can get a common denominator there of getting a 3, so 128 over 3 minus 24 over 3 will give me a value of pi times 104 over 3. And so our final volume would just be 104 pi over 3. So if you feel that you're doing something pretty similar to what you've done previously finding volumes, you are. You've found the washer method, something that we had to do previously in our curriculum. The difference is that now we're going to be revolving around a line that's not the x-axis, like in this case here, or not the y-axis. And so we have to do a little bit more thinking in terms of identifying what our radii, whoa, hello, something's jumpy around here, what our radii are going to be, and then go to town with the washer formula, so to speak, of finding the volume. So let's take a look at one more here, where we're taking a look at the volume with respect to a line, a horizontal line. And I encourage you to go ahead and pause the video and try to work the example out ahead of me and see what you wind up getting. So presuming that you have taken the time to pause the video and work out the problem, let's go ahead and see what we have here. let's start by graphing the biggest function that we have here. This is going to be the one that may or may not give some people trouble. This is going to be a quadratic function that has been, the vertex has been shifted up 4 spaces, and there is a vertical reflection. So we have something like this here, okay? And we're going to be looking at the line. Let me pick another color here, kind of bright. Y is equal to 0 again. Whoa, that is not what I wanted to do. I wanted that. Somehow I hit something I shouldn't have. There we go. All right, so there's the line y is equal to 0. And the boundary that we're going to be finding the volume of, in this case, is going to be, this is the region that we're looking at. This is what's going to be kind of reflected, I'm sorry, not reflected, but rotated over the line y is equal to -1 in this case. And because we're revolving it around the line y is equal to 0, it's going to kind of go that way. We're going to need, our interval will be along the x-axis again. So let's see what we wind up getting here. Looking at some points, and I know I didn't draw my parabola perfectly, but that's okay. The vertex is going to be at 4, 0. And using the points from the parent function, we can see that, you know, if I have a vertical shift of 2, then my horizontal movement will be, I'm sorry, if I have a horizontal movement of 4, then my vertical, I'm going to get it right this time. If I have a vertical movement of 4 on the parabola, then I will have a horizontal movement of 2 in either direction across the line of symmetry. So at this point here, I'm going to be at -2 and 0. And at this point here, I'm going to be at +2 and 0. Now, in this case, that would give us an interval of -2 to +2 on the x-axis. Or you can do the interval from 0 to a +2 if you like having that 0 as your lower bound, but you have to double this for the symmetric nature. You have to double that for the symmetric nature of the parabola. So let's see if we can identify the inner and the outer radii. Well, the outer radii, let's say, is going to be, let me see if I can get kind of a darker color here for the outer radius. The outer radius, you can imagine that, you know, from say like around here close to the vertex or anywhere on the actual curve of the parabola itself is going to be coming down here. So just like what we saw in the last example, we are going to take the difference of the uh, boundary, the function that it's going to be, and its line of rotation. So in this case, the boundary that we have is the 4 minus x squared, and we're subtracting the line y is equal to -1. So that will simplify to be 5 minus x squared for the outer radius. And so for the inner radius, let's pick another color here. The inner radius is going to be about here. That's going to be from the other boundary line, y is equal to 0, to the line of that we're going to be rotating around. So here, the boundary line is going to be 0. And, whoa, I don't know why my computer keeps wanting to jump around like that. So my boundary line for my region is 0, and we're going to subtract the line that we're revolving it around. So in this case, the radius here is going, oops, I mean to write r for radius is just going to be a +1, and it makes sense because the radius has to be it represents a length, and lengths are going to be positive, so the inner radius should be a positive number even though we're below the x-axis. And again, this is going to rely on us using the washer method. So we're going to set it up by saying volume is equal to pi. And in this case, I'm going to go ahead and do 2 pi because I want to keep my lower bound to be 0. So I'm going to use the symmetric nature of the parabola and double just kind of like the one side of the parabola. And we'll say 2 pi from the interval of 0 to 2. And we're going to say 5 minus x squared squared minus the inner radius, which is just 1 squared dx. And now simplify the integrand and then try to do the antiderivative. So here we'll get volume is equal to 2 pi. And when we distribute the binomial, we're going to wind up with putting it in standard form. I'm going to have x to the 4th power minus 10x squared plus 25. And of course, 1 squared is going to be minus 1. So we'll just go ahead and change that 25. We'll just go ahead and subtract the 1 from it and make it 24 dx. And so now we have a relatively simple, straightforward polynomial that we can take the antiderivative of. So let's go ahead and do the antiderivative now. And here I'm going to get 1/5 x to the 5th minus 10/3 x cubed plus 24x evaluated from 0 to positive 2. And then at this point, it's just a matter of plugging and chugging and see what the arithmetic gives you. So let's say 1/5 times 2 to the 5th minus 10/3 times 2 cubed. That's not a very nice 3. Plus 24 times 2. And of course, the whole point of doing the symmetric nature is to keep that lower bound to be 0. So effectively, we don't need to do the substitution with the 0 because everything's going to simplify to be 0 since the entire integrand has x, or the antiderivative, everything has x's on it. And just keep going and see what you wind up getting. So 2 pi. So we're going to have 1/5 of 32. So that'll be 32 fifths here. Negative 10 minus 2 cubed, so that'll be minus 80 over 3 and plus 48. And I know you should be able to do the arithmetic here without a calculator, but if you need a calculator to get a common denominator to work the fractions for you, I wouldn't hold it against anybody. The common denominator obviously is going to be 15, so if we get a common denominator, this would be 96 minus 400 plus 720 all over 15. And that would give us, when we simplify everything inside of the parentheses, that'll give us 416 over 15. And we multiply that by 2 pi, and our final answer will be 832 pi over 15 cubic units, whatever they happen to be. So we're going to go ahead and stop this video here. We are going to do a couple more examples where we're going to be rotating something horizontally, meaning that we're going to be rotating across a vertical line instead of a horizontal line. But Until then, guys, thanks for watching. Take care. Be safe.